At the previous lecture we discussed linear systems and we considered Gaussian elimination, so this is the way that allows to solve a system of linear equations and to find the general solution of such a system. And we introduced the notion of a reduced row echelon, of a row echelon form of a matrix of linear system, and we considered a special form of this row echelon form that was called reduced row echelon form. And so we proved a very important theorem that every matrix can be transformed into row echelon form and into the reduced row echelon form by applying elementary row operations. And so we used this method for solving some particular linear equations. And now we'll continue to discuss reduced row echelon form. And first of all, I'm going to prove that reduced row echelon form is uniquely defined for a given matrix. So this is not true for just row echelon form. So there could be different row echelon forms of the same matrix, but that's true for reduced row echelon form. So the first subsection today would be the uniqueness of reduced row echelon form. So I'm using green for the titles. So, theorem that we are going to prove for any matrix A from our set of matrices with n rows and m columns. The reduced row echelon form is uniquely defined. So this is what we are going to prove. We are going to prove this by contradiction, so let A be a matrix with n rows and m columns, and assume it has two different reduced row echelon forms R and S. So we're going to prove that this is not possible. So the first thing I'm going to mention that the leftmost column of these two matrices is the same. Of these matrices is the same. So according to the definition of a reduced row echelon form, so there could so the first column, the leftmost column, is either a zero column or it should have the only non-zero element in the 1-1 position, just because otherwise we will have a contradiction with the definition of reduced row echelon form. So indeed, let me explain this. This column has either the form only with zeros, or the form 1 and then zeros. Because otherwise, by applying elementary row operations, we can transform our matrix to a matrix with either this with either such first column or such first column. Okay, so in the first case, so if the first column looks like this, then the matrix A, the initial matrix, has only zeros in the first column. If there is at least one non-zero element, it is not possible to get rid of it by applying elementary row operations. And since there is at least one zero element, so it is also not possible to get rid of it by bringing our matrix to another row echelon, to another reduced row echelon form. So this means that both R and S have also zero first column. Okay, so either we have this, either we have the first column of this form for both matrices, or we have the first column of this form for both matrices. So we assume that our matrices are different, so there exists some different columns. So let J be the smallest number such that the jth column of S is not equal to the jth column of R. So we know that J is greater than 0, just because the first column is the same. Okay, so now we're going to construct a pair of matrices. So for the matrix R, construct the matrix R with a hat by taking only those columns of R that contain leading elements and that are to the left of the jth column of this matrix. So we take only these columns and the jth column itself. So what does this mean? So let me consider a diagram. So if this is our matrix R that has reduced row echelon form. So we have, for example, we have 1 and then zeros here, and we have something here. So we have this staircase structure, and somewhere here we have the jth column. So we take only the columns that contain leading elements. So this is the leading element, then we have leading element here, we have leading element here, and so on. So we take only the columns with leading elements that are to the left from the jth column and the jth column itself. And so we put these columns into a new matrix, and we call this matrix R with a hat. So by the same principle, construct the matrix S with a hat from the matrix S. So let us look at those matrices, and now I'm going to consider different cases of the forms they can have. So let us R with a hat. So there are two possible options. So either this matrix has the form where we have the identity matrix here, then we have 0 here, zeros, then we have zeros here, and we have something here. I'll denote this column by R. So this is the first option, or another option is that we still have the identity matrix of the size k by k here. We have 1 here, then we have zeros here. But in this case, since this is this matrix has the reduced row echelon form, in this case we should have only zeros here. So there are two possible options for this matrix. So we have the identity matrix here just because we take only columns with leading elements from the original matrix, and this matrix has the reduced row echelon form. This means that we have only zeros above the leading elements. So that's why we have the identity matrix here. Okay, so this is so these are two possible forms of the matrix R. So similarly, the second matrix can have also such a form. So either S has the form with the identity matrix here and some non-zero column here, or sorry, S with a hat, or S with a hat has this form with zeros here and with 1 here. So there are two options. Okay. And now we will prove that, in fact, either both of them have this form or both of them have this form. So this is what we're going to do. So what do we know about these matrices? So we know that the matrix R is obtained from the original matrix A by a series of elementary row operations. So all elementary row operations, as we discussed previously, are invertible, so we can go back, and that's why matrices A and R are row equivalent. So each one of them can be obtained from the other one by a series of elementary row operations. So similarly, A and S are also row equivalent. And that's why matrices R and S are row equivalent. Okay, and then we just excluded some columns of these two matrices, I mean of R and S, and we obtained, by doing this, we obtained matrices R with a hat and S with a hat. That's why R with a hat and S with a hat are also row equivalent. Okay, and now consider linear systems such that matrices R with a hat and S with a hat are their augmented matrices. So we think about this column as the column of the right-hand sides. Okay, since these matrices are row equivalent, the systems are also row equivalent. So the systems are equivalent. And this means they have the same solution set. Okay, but if we assume that one of the matrices has the form I will denote, for convenience, I will denote this form by 1 and this form by 2. So if we assume that one of the matrices have the form 2, then the corresponding linear system is inconsistent, because the last equation has the form 0 equals 1. So, since these two systems are equivalent, the other system should also be inconsistent. And this means that the other matrix has the form has also form 2. So the other matrix has form 2. So they both has this form and they are equal. So S with a hat equals R with a hat. So we come to a contradiction. So now we say that, so now we can claim that both matrices have the form 1. So both R with a hat and S with a hat have form 1. And what does this mean? So if we look at this from the point of view of the system, so the column R is exactly the solution of the corresponding system here, and the column S is exactly the solution of the corresponding system, just because we have the identity matrix here. So in this case, S and S lowercase and R lowercase are the solutions of corresponding systems. But we know that these systems are equivalent, so their solutions are the same. So we conclude that R equals S, and therefore R with a hat equals S with a hat. Okay, so we come to a contradiction, because we started from the assumption that there is some column in this matrix that is different. And so we consider the leftmost column that differs in these two matrices. So we, starting from these matrices, we consider two new matrices, R with a hat and S with a hat, and we come to a conclusion that they are equal. So this is a contradiction, and so the theorem is proved, and now we know that the reduced row echelon form is uniquely defined for any matrix with real entries. Okay, so now we'll move on to the third section of this chapter, the inverse matrix. and the first subsection would be invertible matrices. So we're going to start with the definition. A square matrix A is called invertible if there exists a matrix A to the minus 1 such that A multiplied by A to the minus 1 equals A multiplied by A to the minus A multiplied by A to the 1 to minus 1 multiplied by A equals the identity. So in this case our matrix is called invertible. So later we will prove that for square matrices one of these relations implies the other one, but just at the beginning we will consider both of them. So we'll call a matrix invertible if both of these relations are satisfied. And first of all, let us start from a series of examples. So obviously not all matrices are invertible. So the trivial example is that that the zero matrix is not invertible. That's trivial, just because if we multiply a zero matrix by any other matrix, we will get the zero matrix. The problem is that even if our matrix is non-zero, it also can be not invertible. So non-zero matrices can also be not invertible. So let us consider also rather trivial examples. So 1, 2, 0, 0. Okay, and so if I try to multiply this matrix by any other matrix with arbitrary entries A, B, C, and D, so I will get something here, and the problem is that I will get the row of zeros here. So I will not even write what do we have in the first row, just because we have the row of zeros here. So this matrix, so this product can never give the identity. Okay, so if our matrix has a row of zeros, it is not invertible, and by the same argument we can say that if our matrix has a column of zeros, it is also non-invertible. Okay, but what if there are no zero rows and no zero columns? So in this case our matrix can also be non-invertible. So even a matrix with no zero rows or zero columns can be non-invertible. So let us consider a matrix with entries 1, 2, 2, 4. And I'm going to try to find a matrix with unknown entries A, B, C, and D, such that the product is the identity. So I'm going to multiply it by A, B, C, and D. So I need to make some computations. So I'm going to get A plus 2 times C here. I'm going to get b plus 2 times d here. Then I'm going to get 2 times a plus 4 times c here. And I'm going to get 2 times b plus 4 times d here. Okay, and so this matrix is supposed to be the identity. So we get a number of equations. Actually, we have a system of 4 linear equations, but I will not write down all these equations. So in particular, relations a plus 2 times c equals 1 and 2 times a plus 4 times c equals 0 should be satisfied. But obviously the second relation is just twice the left-hand side of the second equation is just twice the left-hand side of the first relation. So divide the second equation by 2. So we get equation of the form a plus 2 times c equals 0. So there are no solutions. Okay, so this example shows that even a matrix with no 0 rows or no 0 columns can be non-invertible. Okay, and finally let us consider some example of an invertible matrix. So let A be a matrix with entries 1, 2, then 1, 3. So, and consider B with entries 3, 1, minus 2, and minus 1. So let us multiply these two matrices in both possible orders and see what happens. So A multiplied by B is 1, 2, 1, 3 multiplied by 3 minus 2 minus 1, 1. So what do we get here? We get 3 minus 2, which makes 1. Then we get 0. Here we have 3 minus 3, also 0. And here we have minus 2 plus 3, 1. So this is the identity. And in the same way, I'm going to multiply B by A. So we have 3 minus 2 minus 1, 1. And so in this case, I'm going to have 1. Then I'm going to have 0. I'm going to have 0, and I get 1 here. So in both cases, we get the identity. And therefore, A is invertible. So at least some matrices are invertible. That's, of course, that's trivial because the identity is also invertible. But so here we have at least one non-trivial example of invertible matrices. So the question, which matrices are invertible, is not trivial. So we will not give the answer to this question today, just because we will need to develop some technique that gives the answer to this question. But in a couple of lectures, we will have the answer. We will have the complete description of all invertible matrices. Okay, but so now we have examples, and let us prove a very simple proposition. So let A be invertible, then A minus 1 is uniquely defined. So there cannot be two different matrices with this property. So assume the contrary. Assume there are two different matrices A to the minus 1 and A tilde to the minus 1 such that I'll denote this by this kind of a star, so such that this relation is satisfied for both of them. Okay, then consider A tilde to the minus 1. So I can represent it as A tilde to the minus 1 times the identity, just because multiplication by the identity changes nothing. And then I'm going to represent the identity as the product of A and A to the minus 1. So this follows from our relation. Then I'm using the associativity property, so this is A tilde to the minus 1 multiplied by A multiplied by A to the minus 1, and according to the definition of A to the minus 1 tilde, this is the identity, so we get the identity matrix multiplied by A to the minus 1, which is just A to the minus 1. And so we come to the conclusion that A tilde to the minus 1 equals A to the minus 1. So this proves our proposition. So now we know that a matrix with this property is uniquely defined, and we can give another definition. So if A is invertible, then A to the minus 1 is called the inverse matrix. Okay, so note that here we consider only square matrices. So it is possible to consider relations of this kind for non-square matrices, but in this case these two matrices should not be equal. So it is possible to consider left inverse matrices and right inverse matrices. So I mean, it is possible to consider a rectangular matrix A with the property that there exists some matrix that the product of A by this matrix from the left gives the identity, and such that there exists the right inverse, so there exists another matrix such that the product of A by this another matrix from the right also gives the identity, but these identities would be matrices of different size in this case, so it is not possible to say that they are not equal, that they are equal. But we are not going to consider these details, so we will not need this within the frame of our course. So when talking about inverse or invertible matrix, we will always assume that The matrices are square matrices in this case. Okay, and now I'm going to make one important remark. So let A be invertible. Then any linear system A multiplied by x equals B, then any linear system of this form has a unique solution. Why? So I can multiply this relation by the inverse matrix from the left. So this means that x equals a to, I will just write it from the right to the left for convenience. So if I multiply this relation by a to the minus 1, so I get a to the minus 1 multiplied by b equals a to the minus 1 multiplied by a by x. So this is the identity. So I get I multiplied by x, and I get I. So x is uniquely defined as the product of a to the minus 1 by b. So defines the solution uniquely. Okay. So just to sum up everything, so we define the invertible matrix, and we proved that if a matrix is invertible, then the inverse is uniquely defined, and in this case, any system with an invertible matrix as any system having an invertible matrix as its matrix of coefficients has a unique solution. And now, right now we do not have any tool to understand whether a given matrix is invertible or not. And right now let us discuss the way how to find the inverse. Okay, so let A be invertible. So we need to find its inverse. So this matrix should satisfy the following matrix equation. So A multiplied by some unknown square matrix gives the identity. So if we manage to find such matrix, it satisfies one of these relations. So after that we need to prove that this matrix also satisfies the other relation of this kind. So, but let us first look at this relation. So what can we say about this? So it is equivalent to n linear systems of the form A multiplied by the jth column of the unknown matrix A equals the jth column of the identity matrix. So J ranges from 1 to n. So we have n different linear systems for the entries of the unknown matrix, and all these systems have the same matrix of coefficients. So this is just our matrix A. And since A is invertible, A to the minus 1 is uniquely defined. So all these systems have a unique solution. So this would be important for finding the method of obtaining the inverse. So we know that all these systems have a unique solution, and all of them have the same matrix of coefficients. So what do we need to do in order to solve any of them? We need to transform the matrix A to reduced row echelon form. This will give us the solution. But we can do it uniformly for all the matrices. So we can apply the same elementary row operations for all n systems. So we can consider we can consider these systems not separately, but we're going to consider them all together. So consider these systems together. Just by writing here the matrix of coefficients and then writing the identity matrix. So here we attach n different columns of the right-hand side. So we have the matrix of coefficients, and in the case of one linear system, we attach just one column of the right-hand sides, and here we have n different systems, so we attach n different columns of right-hand sides, and so we will apply elementary row operations. So apply the same elementary row operations. So when we solve the system A multiplied by the jth column of x equals the jth column of the identity matrix, we start with the augmented matrix A. We put A here, and we put the jth column of the identity matrix, and then we apply elementary row operations, and finally we get the identity matrix here. And why do we get the identity matrix here? So we know that the system has a unique solution, and if a linear system with a square matrix has a unique solution, then its matrix, then the reduced row echelon form of its matrix of coefficients is just the identity matrix, because we have no free variables. So there are no free variables. That's why all the variables are leading ones, and it follows that the corresponding matrix is just the identity. So when we apply elementary row operations to such augmented matrix, we get the identity matrix here, and here we get some column C sub j. And this is the solution, where C sub j is the solution of the system, and therefore it's just the jth column of the identity matrix. Is the jth column of the identity matrix. Okay, so what do we do here? So finally we consider such matrix. We apply the same elementary row operations to all the matrices. Finally we get the identity matrix here, and in all the matrices, in all these matrices, we get the columns of the inverse matrix here. So when we put all of them together, we just get the inverse matrix here. So this is the algorithm. So we consider such a pair, and we apply elementary row operations to both matrices. And so when we come to the identity matrix here, which sometimes happens just because we assume that our matrix is invertible, and that's why the solution is unique. And so in this case we get the inverse matrix here. And of course we need some examples, so let me consider some example of finding the inverse. So I will consider a 3 by 3 matrix with entries 1, 2, 1, 1, 3, 2, 2, 1, 0. Okay, so let us apply this algorithm. So consider a pair. So I take this matrix 1, 3, 2, 2, 1, 0, and then I attach the identity matrix here. Okay, so I'm going to apply elementary row operations in order to get the identity matrix here. So I will subtract the first row from the second one, and I will add the first row multiplied by 2 to the third row. So we keep the first row unchanged. Then here I get 0, 1, 1, minus 1, 1, 0. So since these are just right-hand sides, so I should apply the same elementary row operations to the matrix that is in the right-hand side as well. And so I get 0, then I get 1 minus 4 minus 3 here, then I get minus 2 here, then I get minus 2 here, 0 and 1. So this is what I get after the application of these two elementary row operations. Okay, then I'm going to add the second row multiplied by 3 to the third one. So we keep the first two rows unchanged. So we get 0, 0, and minus 2 plus 3 makes 1 here. So we get minus 2 minus 3, which makes minus 5. Then we get 0 plus 3, which makes 3, and we get 1 here. Okay, so this is row echelon form, but not yet reduced row echelon form, so I subtract the last row. So I'm going back from the right to the left here in order to kill all the elements in the upper triangle of this matrix. So I subtract the third row multiplied by just 1 from the first row and from the second row as well. So we get 1, 2, 0, then we get 6, minus 3, minus 1, then we get 1, 0, 0, 1, 0, so we get 4, then minus 2, and then minus 1, I guess. And so the last row is preserved. It's minus 5, 1. Okay, and so the final step is to subtract the second row multiplied by 2 from the first one. So we get 1, 0, 0, and then here we have minus 2, then minus 3 plus 4, which makes 1, minus 1 plus 2, which also makes 1. So, and the two remaining rows are preserved here, so 0, 0, 1, minus 1, 3, 1. Okay, so now we find the solution of the following problem. So we cannot yet claim that this is the inverse just because we need to check both relations. So what relations? So this matrix multiplied by the original one from the right and from the left should give the identity. So right now we can, so we claim that, so let me denote this by B. We claim that B is the solution of matrix equation A multiplied by X is the identity. So it is the right inverse in some sense. And then one may multiply, or just one may verify that B multiplied by A gives the identity as well. So I will not do this just because these are just simple computations. But so one may do this, and this altogether, this gives the identity matrix. So later we will prove that it is enough just to apply this procedure, because the existence of right inverse or left inverse implies the existence of, implies that that our matrix is invertible, if our matrix, of course, if we consider square matrices, of course. Okay, so this is an example showing the standard procedure that allows to find the inverse. Okay, and so the next thing that we're going to discuss would be, subsection 3.3, matrices of elementary row operations. Okay, so let me formulate and prove a rather simple proposition. So let A tilde be obtained from A by a series of elementary row operations. Then there exists a square matrix U such that A tilde equals U multiplied by A. Okay, so let us prove this proposition. So there are three types of elementary row operations. So what happens to our matrix if we multiply its row by some scalar? So in fact, this corresponds to multiplication of our matrix by some particular matrix from the left. So consider multiplication of the ith row by some real number. So it corresponds to multiplication by some matrix from the left. I'll just write down this matrix explicitly. So consider matrix that has 1 everywhere on the principal diagonal besides lambda in the ith row, and then so here we have 1, 1, and here in all positions we also have 1. So the only element on the principal diagonal that is not 1 is just on the ith row. And all other elements are zeros here. And so when I multiply our matrix by the original matrix, so what happens? So we take a row from here and we multiply it by columns. So you see that here we have 1 and then zeros, so the first row remains unchanged. The second row remains unchanged as well, and so the only change will happen when we take the ith row of this matrix. So when we multiply the ith row of this matrix by all columns of our matrix A, then the elements that are on the ith position here, that is the elements that are in the ith row, are multiplied by lambda. So we're going to get lambda times A I1, etc., lambda times A IN. And so all other rows of this matrix remain unchanged. So this type of elementary row operations corresponds to multiplication by matrices of this kind from the left. Okay, so the same for two other types. The same happens with elementary row operations of two other types. So when I multiply our matrix by a matrix which also has 1 everywhere on the principal diagonal besides 2 positions where we have zeros, and we have 1 in all other places. So assume that we have 0 here and 0 here so we have 0 on the II position, and we have 0 on the JJ position. Instead of these, all other elements outside the principal diagonal are zeros, except for the 2 elements here. So we have 1 here and we have 1 here. So we have 1 on the JI position and 1 on the IJ position. And so when I multiply this matrix by A, what happens? So nothing happens when I consider rows that are different from the ith and the jth rows, and so I'm going to get A11, etc., A1n here. And what happens if I take the ith row here? So I have the only non-zero element on the jth position here. So instead of the ith row, I'm going to get the jth row here. So A sub j1, etc., A sub jn. So this would be the new ith row, and the new jth row would be the former ith row by the same argument. So this matrix swaps the 2 rows. Okay, and finally I need to find a matrix that corresponds to the last type of elementary row operations, that is adding one row multiplied by a constant to another row. So in this case the matrix will have the form, so I'm going also to have here I'm going to have 1 everywhere on the principal diagonal, and so for example this would be the ith row, and besides 1 here, I'm going to have lambda on the jth position in the ith row. So consider such matrix and multiply it by A. So what happens when we carry out this multiplication? So all rows except for the ith will remain unchanged. And what happens to the ith row? So here we take the element that is on the ith position, and so when we multiply columns of the matrix A by the ith row of this matrix, so we take the elements that are on the ith position in every column, and we add the element that is on the jth position multiplied by lambda. So this is exactly adding the jth row multiplied by lambda to the ith row. So I'm going to get A sub I1 plus lambda times A sub J1, etc. A sub In plus lambda times A sub Jn here. And so all other rows remain unchanged. So we see that every elementary row operation corresponds to multiplication by some matrix. So let me just write it explicitly. So hence, every elementary row operation corresponds to multiplication by some matrix. Okay, so when we apply the series of elementary row operations, we get our reduced row echelon form. So what happens? So first, we take our matrix, then we multiply it by some elementary matrix. And so when we apply the series of elementary row operations, we multiply by product of elementary matrices. So we will call matrices that we just derived elementary matrices. So the matrices that correspond to various elementary row operations. So these are elementary matrices. So we multiply A from the left by this product, and we get the reduced row echelon form by doing this. So in order to find such matrix, I need just to denote the product of elementary matrices by U. So we prove the existence of such matrix. Okay, so this proves our proposition. Okay, so I need to make some remark here. So all elementary matrices are invertible. It is more or less obvious just from the construction, because elementary row operations are invertible. So matrix should be, so all the corresponding matrices should be invertible as well. But it can just be proved straightforwardly. So, for example, I will not go into the details, just because it is more or less obvious that if I take matrix that corresponds, if I take a matrix that corresponds to the first type elementary row operations, so with lambda here, and so the inverse and with zeros everywhere else. So the inverse would be obviously given by a matrix that has 1 here, 1 everywhere, besides on the principal diagonal, besides 1 over lambda on the same position. So obviously if I multiply these two matrices I get the inverse. So this corresponds to the fact that in order to carry out the inverse elementary row operation, I need to divide the row by lambda, right? So when I swap the two rows, so we have 1 and 1 here, and so the inverse is given by the same matrix. So this matrix is self-inverse, which corresponds to the fact that we need to apply this, we need to apply these elementary row operations twice in order to get the initial matrix. And so what do we need to do in order to invert the third in order to invert an elementary row operations of a third type? So here we have 1 everywhere on the diagonal, and so we have in the ith row we have 1 and lambda here on the jth position. So what do we need to do in order to perform the inverse operation? We need to subtract the jth row from the ith row, so we get 1 everywhere on the principal diagonal, including the ith position, and here we are going to have minus lambda. So it is not difficult to check that all these matrices are just inverses to the matrices of elementary row operations. So now I will prove some other very important proposition. So let A be invertible and consider a sequence of elementary row operations transforming A to the reduced row echelon form. Then the product of corresponding elementary matrices is the left inverse for A. So in fact it is the inverse, but we did not prove yet that the existence of the left inverse implies the existence of the inverse, so we'll prove it a bit later. But so that's why now we just prove that the product of these matrices being multiplied by our matrix from the left gives the identity. So this is what we're going to prove. Okay, so since A is invertible, its reduced row echelon form is the identity. So consider the sequence of elementary row operations, bringing this matrix to the identity. So we start from the initial one, then we apply some poor notation just because you denotes the matrix, so some elementary row operation E1, then etc. So then after applying the kth elementary row operation we get the identity. So this is what happens. And so since we know that each time when we apply an elementary row operations we multiply by some matrix from the left, so each time we apply a transformation, we multiply by a matrix from the left. So according to what we have already proved, so the reduced row echelon form, which is I, is the product of U sub k times U sub k minus 1 times etc. times U1 multiplied by the initial matrix. So the product of these matrices, I'm going to denote it by U. So again, so the product of these matrices gives exactly the left inverse. Or, to be more precise, one of the left inverses, just because we did not prove yet that left inverse is uniquely defined. Okay, so we get another way to find the inverse. So just by multiplying elementary row operations. Of course, that is not convenient to use in practice, so the algorithm that we discussed before is much more convenient for practical finding the inverse. Okay, so the next thing I'm going to discuss would be a bit technical. So it would be 3.4, I guess. So inverse and transpose of a product. So here I'm going to prove two simple propositions. So the first of them states that the product of invertible matrices is also invertible. So let A1 etc. AK be invertible. Then their product is also invertible, and the inverse to the product is the product of inverses, but in the reverse order. So this is what we are going to prove. So the proof would be very straightforward. So consider this product and multiply it. So consider A, which is the product of the inverses in the reverse order, and I'm going to multiply it by, I'll better denote it not by A but by B. So I'm going to multiply it by the original matrix from both sides. So B multiplied by A1, etc., AK by this product is just AK to the minus 1, etc., A1 to the minus 1 multiplied by A1, etc., AK. So we'll look at what happens here in the middle. So we have the inverse to the first matrix, so this gives the identity. Okay, so after one step we get the product of the following form: AK to the minus 1, etc., A2 to the minus 1 multiplied by A2, just because these guys make the identity, and so AK in the end. So this product is also the identity, and so by continuing like this, we're going to get the identity. So in the same way, we consider the product in the reverse order. So A1 multiplied by AK multiplied by B gives the product A1, etc., AK by AK to the minus 1, etc., A1 to the minus 1. So this matrix gives the identity, and so on. So in the same way we get the identity. That's why this product is the inverse. Okay. So this is the first proposition, and the second proposition would be about the transpose to the product of matrices. So here we consider only square matrices, just because we're talking about invertible matrices. So let A1, etc., AK be matrices such that the product A1, etc., AK exists. This means that the number of columns in every matrix should be the same as the number of rows in the next one. In this case, we can multiply these matrices. So then the transpose to the product, so the transpose to the product of all these matrices is equal to the product of the transposes, but in the reverse order. So this is what I'm going to prove. So let us prove this proposition. So consider the product of two matrices first. So I'll denote so that A be a matrix with n rows and m columns, and let B be a matrix with m rows and p columns. So it is possible to multiply it in this order. So C would be the product of A and B, and D would be the transpose of C. So then, what is the jth ith element of the matrix D? So since it's C transpose, it is C sub ij for every pair of I and j. So what is this element? So this is the element of the product. So this is the sum where k ranges from 1 to m of a sub I k multiplied by b sub k j. Okay, so this is what we have here, and then I can rewrite it like this. So what is the ith element of the matrix A? It is the kth ith element of the matrix A transpose. So A transpose ki multiplied by B transpose jk, right? Okay, and so these are just numbers, so they commute, so I can rewrite this sum in the form B transpose jk it down like B transpose, and so the jth kth element of B transpose multiplied by the kth ith element of the A transpose. So and now we can see that when we compute the jth ith element of the matrix D for every pair of j and I, so we multiply the row of this matrix by a column of this matrix using the standard rule for product of the two matrices. So therefore D is just B transpose multiplied by A transpose. So this proves our claim for the product of two matrices. And for more than two matrices, use induction. So denote the product of matrices, so denote the product of matrices starting from A2 by B. So what are we going to do? What are we going to get in this case? So the transpose to the product of all these matrices is just the transpose of the product of A1 and B. So we know that the transpose of the product of the two matrices is just B transpose by A transpose, and so then we use the induction in order to show that B transpose, so here we have k minus 1 factors, so this is just A sub k transpose, etc., times A sub 2 transpose multiplied by A1 transpose. So this is what we get here, and so this proves our proposition. Okay, so that's quite technical, but we will need this. We will need these propositions further, and so the next subsection will deal with matrices of elementary column operations. So I will just so the subsection 3.5 elementary elementary column operations. So consider a matrix, not necessarily a square matrix. Consider a matrix with n rows and m columns. Let us define elementary column operations. What does this mean? So what are the elementary column operations? So similarly to the case of elementary row operations, there are three types of elementary column operations. So what can we do with columns? So we can multiply, sorry, not the row, but we can multiply a column by some scalar. So we take a column of our matrix. For example, we take the jth column of A and we multiply it by some scalar. We can swap two columns. And we can multiply a column. We can add a column multiplied by a scalar to some other column. So operations of this kind are called elementary column operations. So of course elementary column operations make absolutely no sense from the point of view of linear systems, just because when we apply elementary row operations, we perform some transformations with linear system that does not change the solution set. But so all these operations, of course, change the solution set. But nevertheless, sometimes we will also need to perform elementary column operations, and similarly to the case of elementary row operations, all these operations correspond to multiplying by some elementary matrices, but in this case we are going to multiply by these matrices from the right. So I'm going to formulate a proposition. So let A be a matrix with n rows and m columns. Then applying an elementary column operation corresponds to multiplying by some elementary matrix from the right. So what does this mean? If I apply some elementary row operation to my matrix, then the result is given by a multiplication of the original matrix by some elementary matrix from the right. So this is proved very similarly to the case of elementary row operations. I will just give the corresponding matrices. So proof is similar to the case of elementary row operations. So what are the matrices? So we take a matrix, and when we multiply it by a matrix where we have 1 on the principal diagonal everywhere except for one place where we have lambda, so obviously this multiplies the, so if this is the ith or maybe the jth column, so it was j before, so let me just consider the j here. So I consider such matrix, and obviously when I multiply A by this matrix, I get the matrix such that its jth column is multiplied by lambda, and all other elements remain unchanged. So here I have lambda times A sub 1j and lambda times A sub n j, so all other elements remain unchanged. So this is one of these elementary row operations. In fact, it coincides with the elementary, matrix of elementary column operation coincides with the matrix of elementary row operation. So when we need to swap the rows, exactly in the same case, exactly in the same way, we consider a matrix where we have 2 zeros on the principal diagonal. All other elements are non-zero. They are just ones, and so here we have just 2 non-zero elements outside the principal diagonal, and once again we get the matrix such that the 2 rows are swapped. So A sub 1j, etc., A sub 1i, etc., A sub 1n, A sub nj, etc., A sub ni. So here we have 1 on the jth position and 1 on the ith position. And when we need to add one column to another one multiplied by a constant, so in this case the only difference is that we need to, since we consider columns, we need to put lambda not in the row but in the column. So so I'm going to consider the ith. So this would be the ith column, and I put lambda here on the jth position. So when I multiply this matrix, when I multiply the initial matrix by such matrix, so the jth column multiplied by lambda is added to the ith column. So I get A sub 1, 1, etc., A sub 1i plus lambda times A sub 1j, etc., A sub 1n, A sub n1, etc., A sub 1i plus lambda times A sub 1, not 1, but n sub A sub ni plus lambda times A sub nj, etc., A sub nn. So this is what we get here, and exactly in the same, so this proves our proposition, and exactly in the same way as we did before, we can say that the product, the product of or maybe it's better to say that composition of elementary column operations corresponds to multiplication of our initial matrix by a product of matrices from the right. Okay, so we'll stop here and we'll continue to discuss some more important results on invertible matrices at the next lecture, and then we will need somehow to develop tools that will enable us with the possibility to answer the question that was posed earlier. So the question how to describe all invertible matrices. Okay, so that's it for today.